Hello, everyone. Thank you for joining. My name is Ujjwal Ratan. I'm a principal SA for machine learning in the global healthcare and life sciences team at Amazon Web Services. Today, I'm going to talk to you about the role of artificial intelligence and machine learning in healthcare, and specifically how AWS is closing the gap and bridging the gap between advanced research and adoption of AI and ML into regular healthcare and life sciences business problems. Before I begin the talking about the specifics of how AWS is bridging that gap, I wanted to set this up by giving you a preamble into how machine learning workloads work. And the whole idea behind machine learning is to not give specific instructions to the processor to actually process. These are learned by algorithms. Those algorithms can be deployed as models to predict based on the learnings that that model has made. And the way this works is through a life cycle. So it starts with the data set. That data set goes into a training cycle. The training cycle would basically expose different elements and features of the data to an algorithm. The algorithm would then get positive or negative reinforcement based on how it's behaving, and learning those elements. If it's learning the right things, it'll get a positive reinforcement and vice versa. And then as the training is complete, what you end up is a model. This model can then be deployed in an active workflow, and that deployment would results in inference. And inference is something that's done on the data that the model has never seen. The key element here is to get that data back into a feedback mechanism to a training set, because that allows the model to continuously improve. And this cycle continues. There's no end or beginning to this. The cycle is continuously taking different aspects of these data sets and reevaluating your model and making it better by various trial and error and other techniques that data scientists regularly pursue for a given use case. Uh, to make this process simpler, AWS has a series of services, which I'm going to talk about today, specifically how it relates the context of a healthcare and life sciences use case. So, in terms of like just giving you a few examples of where machine learning and AI can help in the healthcare ecosystem, these are some of the areas where we have actively engaged with customers on. Begins with patient and population health analytics, things around analyzing the spread of a certain disease, analyzing how populations of cohort people that are susceptible to certain conditions would react to a certain medication. All of this requires ingestion of large volumes of data that represents the population, and then use that data to kind of train models that would predict various outcomes for that population. So AI has a big role to play when it comes to patient population health analytics. Moving on to its role in the revenue cycle area, we've already seen, workflows where a lot of these healthcare specific metrics have to be tracked from a revenue perspective, cost perspective, and that requires standardization of data across various interoperability standards, ontologies, coding systems, and that requires a lot of human intervention. By using machine learning makes you be able to automate some of these processes. Quality improvement is also an area where we see traction when it comes to use of machine learning. CMS has various metrics that it tracks different hospitals by, and machine learning can help these hospitals and providers to become compliant with those metrics and become better at getting better ratings on those CMS metrics, like metrics that define mortality risks that a certain hospitals is associated with, or even things like readmission rates. Those are things that typically hospitals would want to keep at a lower rate. And the way you do that is by, training models that predict how these events would eventually happen, and then control those by targeted interventions. Um, Another area where we see a lot of traction when it comes to the use of AI is in PHI compliance. There's a lot of back and forth exchange of information when it comes to building and training models. And sometimes these information contains sensitive data sets needs to be de-identified. And those techniques require either human interventions or operating with the bounds of certain rules. And it's really difficult to actually scale these processes out. So machine learning can help detect PHI or sensitive information in your data sets and build workflows that allows you to mask it or redact it. Um, Also, in terms of operational efficiencies, we've seen machine learning help, as I talked about, in use cases around automation, around the use of different techniques that are requiring a lot of human interventions to automate those processes using set rules or techniques that may be a little difficult to carry out by conventional rule-based engines. And that last icon over there, what else, is intended to kind of draw your attention towards the fact that this is just the tip of the iceberg. I mean, we've been working actively with a lot of customers who have presented various categories of problems that you see listed here, but we feel that there's a lot of unexplored territory here. And our role is to actually make that exploration as easy as possible using some of our managed services. So let me begin this conversation of automation and operational efficiency by giving you some stats around unstructured information. And this is an area where we've seen a lot of customers either rely on conventional rule-based engines or interventions that allows people to kind of process all of these unstructured information together and then make sense of it. And by some estimates, a lot of unstructured information, like close to 1.2 billion unstructured clinical documents that are in the ecosystem every year. And healthcare IT professionals face a critical choice over here. I mean, can they actually scale up their operations and build solutions that allow them to draw information trapped in these clinical documents? And these might be critical information that never get utilized, or can they actually scale up their human workforce to actually process all of this information in a timely manner? If you think about it, uh, if we have to solve this problem, it generally involves around two steps. The first is just extract information from different modalities that generate these unstructured information. And the second one is around understanding. Once it's extracted, how do we actually make sense of what's extracted from all those modalities? So the extraction could be from medical forms, from medical images. It could be from audio transcriptions, because these are all areas where methods by which unstructured information could be generated in the healthcare ecosystem. And then once you've extracted it, you have to make sense of what's extracted. So extraction on its own is a huge problem, because every different type of data sets would pose a different kind of challenge when it comes to the extraction methodology. But once you've even extracted, how do you make sense of what is embedded within those extracted information and what's clinically insightful in those extracted assets? And if you think about it, so these could be things that AI can help with, like in terms of extracting from images. It's a computer vision problem. If it's extracting from audio transcriptions, it's basically a speech to text problem that could be handled via sequence to sequence neural networks. So each of these areas have their own advanced deep learning and machine learning techniques that could be utilized to actually convert all of the unstructured information into a format that could be textual and could be understood by downstream engine. And on step two, when it comes to the understanding of that information, it is in its own a machine learning problem or a deep learning problem around NLP, or natural language processing. So customers who have problems revolving around unstructured information capture, generation, processing, and then even making sense of this have to rely on expertise of a few deep learning scientists or engineers. And that model itself is not very scalable, because as you saw, I mean, there are multiple techniques involved here, multiple components of advanced research involved here, and for a business to actually tap into those resources in time and then scale those operation out and productionize workflows that actually allow them to build custom workflows specific to their business problems is a huge challenge. So from an AWS perspective, let me get into the specifics of how you can execute workflows like this using some of our managed services. So looking at the first step of extraction, if you're acting from medical forms, you can use a service called Amazon Textract. Textract is a service that allows you to actually do OCR on digital documents, and these solutions are built with the intention of these services are built with the intention of keeping it really, really simple to use. So they all operate via simple APIs. People who do not have a lot of understanding of deep learning or machine learning make use of these services with ease. And it has some advanced capabilities of recognizing key value pairs, table detection. So, for example, if you want to go to a certain section of the form or certain field of the form, you can easily detect those fields and extract information in a very precise manner by going to specific areas of forms. And then, this allows you to actually create some sort of an automation built into your extraction workflow from forms, because what this presents as an output is a very predictable, programmatically parsable JSON that you can include in your workflows and go from a structured representation of a form to a structured metadata representation of how that form would look in a JSON representation, and that is easy for you to parse using typical programmatic structures. When it comes to extracting from audio transcriptions, we have a service called Amazon Transcribe Medical. This is an extension of an existing service called Transcribe. Transcribe Medical has been specifically trained to recognize medical information in speech. And the way it works is by creating a persistent connection to the Transcribe Medical endpoint via the WebSocket protocol. You again use the AWS SDK, the CLI, or the console to create that persistent connection. And once you have that connection, you send a stream of audio, and then you get a text as a stream back. Again, the text is represented in a very parsable JSON structure, so you can use that solution to parse that text out and then use it for your downstream processing. When it comes to extracting from medical images, there are a lot of texts that can be embedded within medical image. And we have a service called Amazon Recognition that has text detection capabilities, using which you can detect the bounding boxes of the text and extract it. We recently launched within Recognition the ability to bring your own labeled data to train a custom classifier, if you will. So using this capability, you can train the recognition by your own labels, with your own labels and labeled images, allowing you to build a custom model using auto ML. And all of this requires no machine learning experience to get started with. So this is something that again accelerates the adoption of machine learning and deep learning in medical image-based processing or use cases. Now, when it comes to making sense of all of these different information that you've extracted, we have a service called Amazon Comprehend Medical, which is like the brains of processing all of this unstructured information. It's a natural language processing service that does named entity recognition on various clinical entities. These entities include medication, medical condition, tests, treatments, procedures, anatomy, and protected health information. So using the service, you can call a simple API and it'll tell you what are the various medical entities as you see listed in that blurb of text. It also goes on to extract relationships between those entities. So if you have, let's say, a medication and a dosage mentioned within the blurb of text, it will relate the two. And another example might be test and a value for that test. So all of those would be related together using deep learning based contextual and relationship extraction. We also have the ability to extract some traits about the entity. So traits could be things like negation. Let's say a certain medication is mentioned in the context of negation. An example might be a patient is not taking a certain medication, or maybe a negation in terms of diagnosis. So let's say a patient did not emit of a certain disease. Those are things that are really important to be caught in the context of negation, because even though there are entities mentioned, if you do not catch it in the context of negation, downstream processing might be hampered because you might treat this as a true positive case of a certain event happening versus certain event not happening. So this just gives you a more context, a lot of more context around how that entity will be mentioned in that blurb of text. We recently launched temporality as a feature within Comprehend Medical. So this allows you to extract temporal attributes about that entity. An example might be a test being carried out on a certain date, now be related to that entity, in this case, the test. All of those would be presented to you in a hierarchical JSON fashion that you can then parse. Diagnosis, signs, or symptoms could also be something that related to an entity as a trait. And all of this are presented as a list. So you could have a trait list that are then associated to a set of entities, and then you can build logic to extract those traits programmatically. It's worthwhile to say that this service was actually HIPAA eligible at launch, and it's completely stateless, which means that you are able to pass PHI through the service. And while you're processing this, you don't have to worry about the existence of any data that may be left behind that you pass through the service, because the service is completely stateless. As soon as you call that API, you see an output, and all traces of the data that's passed to create that inference for you are removed, and nothing is saved on Amazon's side in terms of that payload or that data set. The idea of all of this is to create a simple API call that allows you to distill complex information by the help of programmatic techniques that do not necessarily involve or have a prerequisite of learning advanced deep learning based processes. So if I have to put it, put some of these things into perspective, here's a screen shows how temporality. So in this case, if you look at this row, there was a certain procedure that was carried out on a certain date, and you can have that relationship, being extracted in terms of a temporal feature to this master entity. In the third row, we see EKG as a test, and you can see when that EKG was carried out and some of the outcome data that is now related to that test. And this allows you to basically get a lot more context about how that test was mentioned, what were some of the values, what was the outcome, and so on and so forth. And all of this is done via deep learning processes that do not require you to conform the input to a certain structure or a certain rule. All of this just works out of the box. Using this temporal feature, you can create a timeline patient like this. So let's say there are various dates where the patient has come for repeated visits, or there is a summary note that has been created via across different visits. You can then create like a temporal kind of graph or a chart for the timeline of care for that patient, where different interventions made, different tests were carried out, and visualize it in this manner. Another area that medical terminologies is really important in is the use of ontology. So we have all experienced how interoperability and the use of different coding systems and standardization within the healthcare terminology is really, really important for both upstream and downstream processes. And within Comprehend Medical, we have a feature of extracting ontologies, specific ontologies like RxNorm and ICD-10 from a blurb of text. And that becomes important for a myriad of downstream processes and use cases. This could be in medicine, where drug names needs to be associated to RX norm codes, or it could be into downstream, medical processes or scheduling that require different ICD-10 codes associated with different procedures. And the way it works is again via deep learning based processes. So because it's all leveraging context based learning models, it allows you to leverage relationships to refine the scope of this linking. It also overcomes any typos or abbreviations that might be in those texts, because it's again relying on not specifics of how that text was mentioned, but the larger context of it. Then it understands complex mapping of generic name with brand names. So if there are like drugs or certain medication names that are not very generic, because it uses contextual learning, it is able to kind of map those up and produce accurate codes for it. Similarly, in the case of ICD-10, each of these entities can be mentioned in different contexts, it might contain anatomical relationships. So using deep learning based processes, you are able to understand those relationships and extract the potential codes from it. Contextual information, again, is really important because you would need to understand how that specific diagnosis mentioned or condition was mentioned. By just like saying that in this example, for instance, the word fell has a totally different meaning or a totally different code when it comes to ICD-10 versus from or out of or through a window. And that would change the way in which the codings are identified for this specific thing. Similarly, toe pain in this case, is by itself may have a totally different meaning. And then when you have comorbidities and related things associated to it, you can go more granular and become more specific in the way these coding systems are analyzed and extracted. So Comprehend Medical does support these as dedicated APIs. So we have support for ICD-10 and RX norm as dedicated APIs that we have released as part of the service, with more support coming really. So if you put it all together, this is how the workflow would look. So if you have different, modalities of unstructured information, like in medical images, in scanned documents or transcriptions, you can pass them through different AWS services, recognition, extract, and transcribe medical in this case, and then use Comprehend Medical to understand all of those in different information that have been extracted medically, and then create a repository of these on S3. S3 is a great persistent storage area. As Comprehend Medical is a stateless service and does not have any storage mechanism, it is able to actually use some sort of a persistent storage area within your accounts. S3 is a great service for that because it allows you to actually encrypt that data and make it secure, make it accessible to only the right parties. And then from there, you can branch out into different analytical and query related services that AWS has in its ecosystem. So if you have a need for creating non-relational key value based pair, or storing them in a search context, you can use Elasticsearch or DynamoDB. If you want to kind of use these into queries or transaction processing or data warehousing, you can use Redshift or RDS for it. And then for ad hoc querying, you can use things like Elasticache, Athena, and even Elasticsearch and QuickSight. So all of this allows you to actually go from unstructured information that might exist in different modalities into very structured, queryable data assets on which you can build some actionable intelligence and draw some insights in a more programmatic and automated way. Now, moving on to the role of AI in medical imaging. There's a lot of different areas that we have seen, like radiologists needing help with. And some of this are associated towards or are targeted towards a radiology burnout problem, where radiologists are expected to look at multiple images in a span of a minute or a day that goes exponentially. And some of this is just exhaustive. And if you look at it, AI can help in automating some of these, obvious diagnosis. It's intended for a way in which we can, offload some of these use cases to AI models that can be helpful, instead of just like saying that AI models on its own autonomously can make these decisions. Even in the form of operational efficiency, if you can offload some of these obvious use cases to models, and then just augment the availability of radiology with those models, is great for operational efficiency perspective. So if you look at these various use cases where AI and deep learning has been applied to medical imaging, it usually falls into two categories. And these are medical image classification. So these would be, if you want to classify certain images into different categories. So these could be things like, oh, tell me whether this tumor is malignant or benign, or looking at a X-ray, recognize whether there's a fracture or not. And these are very simple binary classification problems, but this can easily be extended into multi-class classification and problems where you would want to classify certain images in different categories, depending on how you've trained your model. So this is one category of area where deep learning can be useful. The second area where we've seen is segmentation. So in this, what you typically want to do is highlight an area of interest in an image. So that you're looking at a brain MRI and you would want to kind of highlight the appearance in that MRI that radiologists can immediately look at, instead of like scanning the whole image. That would just give them a more, I would say, operationally more efficient way of targeting hundreds or even thousands of these MRIs that they might be seeing in a span of a certain period of time. So using these techniques, AI and ML techniques, radiologists can become better and more efficient in their day-to-day work. And the gating factor for most of these models, it's not technology and computer vision, but it's more around the availability of high-quality labeled data sets. Because when you think about the advances of in the area of computer vision, a lot of this is proven in research. It's been proven to perform really, really well. Um, but when it comes to productionizing it and making it available to customers, a lot of this is gated by the availability of high quality labeled data sets. Um, so we have a service called SageMaker Ground Truth. Ground Truth is a service that utilizes the capabilities of human annotated datasets and active learning pipelines to create high quality labeled datasets for your downstream machine learning and deep learning training. So the way it works is you start with initially annotated human labeled datasets. Those go into an active learning pipe. The active learning pipeline learns from those annotations, and it continues to kind of become better over a period of time as and when more sets are produced. And in the absence of models becoming better, it is continuously routed to the humans. The humans would then look at those images, label them, and then it is continuously fed back into the active learning models as training records on which the model can train. And this continues to happen till the time the model is confident enough to make decisions on what the label is. And as and when these labels are generated, they are scored in terms of how confident or how accurate these models are as far as those labels are concerned. And you can set a threshold. You can say that, if there's any label that is automatically generated that's below a certain threshold, let's say a 90% accuracy, I would want humans to revalidate it. And in that case, it won't be fed into a category of labeled data set. It'll be fed back to the humans who would then validate and check whether the label was accurate or not. And this is something that is quite flexible in the way it works. The human labelers can be sourced from the public or from a private workforce. So you can create a workforce of private human labelers who would have their own dedicated portal using which they can generate these labels that is visually available as a static website. uh, it also works in an entirely um, manual way, so it does not need to actually build active learning pipelines in the loop. In which case, you would just use this as a tool to route it to a set of specific targeted human beings who would look at different images and generate those labels. If you want to use active learning based models to actually automatically label these, it has a mode in which you can switch to and create this active learning capability in your workflow as well. But the point is that you can go from raw data sets that are unlabeled and result in a training set that can directly be fed into downstream training algorithms on SageMaker, and that allows you to create a pipeline where you go from like unlabeled data sets to labeled data sets to a training cycle, and then finally to a deployed model that can start making these decisions quickly. Some of the examples of customers who have been using deep learning capabilities for medical imaging on AWS. These include a company called Matrix Analytics. They built a product called Lung Direct that recognizes pulmonary nodules and classifies them as malignant or benign in lung scans. And they use the AWS Deep Learning AMI to achieve. We also working really closely with GE Healthcare on various medical problems. They use Amazon SageMaker to create different classification and segmentation related deep learning models that run on either the MRI machine or the cloud platform that is powered entirely by Amazon SageMaker tasks. Area where machine learning has a lot of relevance in the space of healthcare is conversational interfaces. And this allows to voice enable a lot of healthcare processes. So these could include process for booking appointments, for example, or for a provider to engage their patients, or for a physician to check his or her appointments. All of this are generally carried out by via portals, and these portals are either internal portals or specific to physicians, or provider portals that are specific to different customers engaging in different areas of the healthcare ecosystem. And these patient engagement or provider engagement or sales, whatever are the areas that you're trying to engage a population in, become really exponentially better when you introduce voice into the ecosystem. It becomes more natural for people to act with those interfaces if it's voice enabled. And we have a set of services, Amazon Lex, which is a conversational interface based service that allows you chatbots. These could be voice enabled or text enabled that you can embed on those portals. And we also have an ecosystem around Alexa that allows you to create cloud-based services that you can embed within your own businesses and into your own healthcare workflows. Now, just to summarize, all that I've been about is just a tip of the iceberg, and our intent, AWS's intent in all of this, is to be the enablers of the availability of these advanced deep learning based techniques and make them easier to be adopted by the healthcare ecosystem. And we do this via, by creating these services that we have been able to launch over years now. And all of this is highly being driven by various things we've heard from our healthcare and life sciences customers. And we basically think tirelessly towards making the barrier to adoption of AI as low as possible. Our mission, kind of AI and machine learning in the hands of every developer, irrespective of the background. Strongly believe the only way we can deploy this is by making it available to as many people as possible. And we do this via a series of AI services that include areas in vision and speech, text, search, and so on, all of them requiring no learning or deep learning expertise. Moving into areas of ML services that are powered by Amazon SageMaker that allow data scientists to build custom models, quickly iterate on hypotheses, create experiments, and create different machine learning models that they can then deploy with a few simple APIs. And then finally, catering to that research community as well by giving them access to deep learning machine images, Amazon machine images, or deep learning containers powered by infrastructure like GPUs and CPUs and our FPGA instances, making them available and accessible to the research community to be used in various research-based and making it easier and accessible to carry out advanced research that ultimately goes into the betterment of these models. So, with that, I conclude my presentation. I again want to thank you for listening. And I would point you to these two links. The first link is the link to our healthcare and life sciences page, where you would see a lot of good information about how we are working with the healthcare customers. And the second link is the link to our homepage for machine learning, where you would see all of our different capabilities in terms of services and customers who have been taking advantage of this. With that, thank you so much again, and uh, have a good day.